All right. Okay, so I'll give you some time to process this. Okay, so so essentially we want to remove disks and over each of these simplices. Okay? And so as long as these simplices sigma, they're just a small set of parameters. So if you move sigma a little bit, then this picture will hardly change. So as long as we somehow remove some disks that stay a bit away from these holes, even if we wiggle a bit on S, these little holes, they won't change too much. Okay? And so we'll do this over simplices of different dimension. And the larger the dimension of the simplexes, the larger the disks are that we remove. Right? And okay, so how do we prove this? The proof here is relatively simple. And it's based on this observation that, on the following observation. So let me take some simplex sigma, and let me really assume that the simplex is really, really small. Then, and just fix some parameter in the simplex. Let me call it S sigma. And let me now look at W as sigma and G bar as sigma. Okay, so this, recall, is isometric to a punctured spherical space form, round spherical space form. And so these punctures here in the spherical space form really correspond to these holes. So within somehow the metric on W, these holes just look like points. Okay? And so what we can just do is we can just let Z sigma correspond to this guy minus a few balls around these punctures. Okay? Okay? So these guys are really these somehow dashed lines are really spheres around the punctures with respect to the metric on W, okay? Because essentially these blue regions, they collapse to a point. And then then we may have some problems if we choose the balls maybe too large so that one ball already covers two of the punctures. Then we don't need to choose too many of. Then we can remove one of these balls. So we can always pass to some kind of sub-selection of these balls that cover all the punctures, okay? And then we can satisfy this property just by choosing the radii larger and larger, okay? So we can choose them maybe by something like 10 to the power of j, where j is the dimension of the simplex. And as long as we somewhere start from a sufficiently small scale, that won't create any problems, okay? All right, are there any questions? Okay. Okay. So now that we have this additional data, these Z sigmas, we can now do the extension process. And the extension process is we're basically working on skeleta of the triangulation of the k+1 disk. Okay? So we are basically proceeding by induction over the dimension of the simplex. Okay? So the goal will now be to find over every simplex to find a continuous family of constant curvature metrics. Let me call it G hat sigma, where S is only contained in sigma, that extend G bar S over the missing disks of the complement of Z sigma. Yeah? Okay, so let me now perform this. So let me fix some sigma. And assume that we've already performed this extension over all the simplices in the boundary of sigma. Okay? And now I need to choose these families of metrics G hat sigma S for every S in sigma. And I want the metrics, want G hat to be equal to G bar on Z sigma. Okay, so I'll define, I should have said G hat of sigma S should be equal to G hat G bar S on Z sigma. So I really only need to make choices on these disks, right? And the construction will be independent over each of these disks. So let me just fix one disk here, okay? So I need to say what the constant curvature metric is on this disk for a fixed sigma and S being contained in that fixed sigma. Okay? And so what conditions do I need to satisfy? Well, essentially, I'm free to choose whatever I want, but I need to satisfy two conditions. First of all, well, if S is in the boundary of sigma, then I've already performed this extension process. So in this case, I would just want G hat sigma of S, let's say restricted to the disk, to be equal to G hat sigma prime of S, as long as S is contained in some sigma prime, which is contained in the boundary of sigma. And then I also want the hat G hat S to extend somehow smoothly to a metric, to the metric G bar on Z sigma. Okay, so I want this to be true near G hat. Okay. But as long as I meet these two conditions, I can choose G hat as I like, right? And then I can work on higher and higher simplices, and then eventually these G hats, they will all fit together to a desired to the desired family. Okay, so the issue is really just satisfying these two conditions if somehow the family of metrics on this disk is already given on the boundary. And so this is a relatively standard lemma, and it may look a little daunting, but it's just something that is basically known. Okay, so let me just recap, just for completeness, of what the lemma is that we need to apply here. Okay, so what I'm going to do here is I'm going to think of this disk, and so we have this nice disk here. And I'm going to choose some epsilon, and I'm going to look at a little annular region around the disk that's still contained in the red part. Yeah. And so let me now focus on this annulus and look at some kind of model case. Okay, so I'm going to assume that our disk, just for simplicity, is contained in R3. So that's the one disk, and I'm looking at a small annulus. Okay, so this is just the previous picture in a simple, just straightened out. And then J, let's say J plus 1 is the dimension of the simplex sigma. Okay, sigma should be diffeomorphic to dj plus 1. So then what we're given is a family of constant curvature metrics parameterized by the entire simplex, or this entire disk, given on the annulus, which is only given on the annulus, only on the red part. And well, on the boundary of the simplex, we've already done our extension. So in this case, we have a constant curvature metric on the entire disk. And so these are two continuous families of metrics. And we have the matching condition that if we restrict H naught to the annulus, then we get H. Sorry, this should be an S. And we have this extra technical assumption. If we look back at the construction of everything, we have this nice property that if we take the just the annulus equipped with any of these metrics HS, then we're actually getting a constant curvature annulus that embeds isometrically onto the round sphere. Okay? So this is not some kind of weird constant curvature metric. It's really just some subset of the round sphere. Okay? So this just follows if you look precisely at what these metrics are. And then the statement of the lemma is then that after shrinking epsilon, there's a continuous map H bar, I should have probably called it H hat, sorry, of metrics parameterized by the entire disk, and that are defined on the entire disk here. So they're parameterized by the entire J plus 1 disk, and they're defined on the entire 3 disk, such that H bar restricted to the annulus is equal to H, and such that H bar is equal to H naught for all S in the boundary of the J plus 1 disk. Okay. So this is exactly what we need in our extension process. Okay. And so how do we prove a lemma like this? Well, it's well known that this lemma is just by some more or less abstract nonsense argument that this lemma is it is equivalent to the Smale conjecture. Okay. So essentially, the Smale conjecture says something about the diffeomorphism group of S3, but this can be reduced to saying something about the diffeomorphism group of the 3 disk relative to its boundary. Okay. And so then we can somehow use something like the exponential map to relate the space of constant curvature metrics on this disk to this diffeomorphism group, and we get that somehow there's no obstruction in finding this extension. All right, and okay, so So let me just go back briefly. So this is some of the lemma that we're using here, and this lemma allows us to extend the constant curvature metric over these disks, and then we get a family of constant curvature metrics on M over every simplex, and these fit together and will give us a global constant curvature family, as we've desired. And so this finishes the proof of the generalized Smale conjecture if M is not equal to S3 or RP3. All right, let me see, are there any questions? So this should conclude this chapter. All right, so let me now move on and try to give you some idea how to prove the some of the general conjecture and also the conjecture regarding the positive scalar curvature metrics. And before doing this, we have to revisit this idea of continuity of families of singular Ricci flows. Okay, so recall in the last class, I showed you how to define continuity of singular Ricci flows, and I called it the quick and dirty method. So the idea was, instead of looking at a singular Ricci flow, we looked at somehow the image of the good points to the time zero slice. So then, and pushed forward the metric on those good points to the time zero slice. So this gave us some kind of partially defined Ricci flow on the time zero slice. And then it was easier to say what continuous dependence means. Okay? But I somehow don't like this method very much because somehow it puts too much emphasis on these good and bad points. And in my opinion, if you're somehow very far in the flow, it shouldn't matter whether the precise world line of the corresponding points hits the singularity or not. Like, so that seems to be too rigid of a condition. Okay, so we don't want to give too much focus on these good and bad points. Yeah? And so instead, I want to do something slightly different, where we really talk about the entire Ricci flow space times as a varying continuously. Okay? So just as a guiding principle, here's this picture again I showed in the first class, where we started from some continuous initial data, and then for every initial data we would get some singular Ricci flow. Yeah? And if I just draw this, I think you would agree with me that we have some kind of continuity. Okay, so for example, as we move from here to here, maybe there's some kind of a protrusion growing out there, which at some point becomes singular. Or as we move from the right to the left, there somehow this neck pinch becomes smaller and smaller, and somehow vanishes within this tip, while the other, some of this branch of the flow will become smaller and smaller. So the extinction here will happen sooner and sooner, and some of this region here will somehow vanish in that singular point. Right? But the difficulty again here is that these singular Ricci flows are only defined up to isometry. Okay, so potentially for every S, we could have manifolds that are MS that are defined using completely different techniques, and and points that have completely different names. Okay, so we will need to find a way to somehow say that these fit into some continuous family, and we'll have to allow for the change of topology. All right, and so to discuss this, let me first discuss somehow a baby case here. So I want to discuss how can we express or define continuous families of manifolds or of Riemannian manifolds. And what I find most interesting here is incomplete Riemannian manifolds. Okay, so the idea, the reason why I find this interesting is due to the following observation. Let's think back at the previous slide where we had this continuous, this hopefully continuous family of singular Ricci flows. Let me now fix some time t and look at just the family of all the time t slices, right? So MST and GTS. This family should in some way depend continuously on S, right? So let me go back to the slide. Let me fix some t here. Then if I look at all the time t slices, I see some sphere. The sphere will become kind of, will grow some kind of nose. And then if I go further to the side, I see a sphere and then something that looks a bit like a point. And then this point will grow out to become another sphere, okay? So in other words, here, the time t slice is a sphere, while here the time t slice consists of two spherical, two manifolds that are diffeomorphic to a sphere. Okay. So the topology of these time slices may change as we vary the parameter. Okay. Maybe another way of saying this is also if we just look at a singular Ricci flow, we have the same issue already. If we change t, then the topology of the time slice may also change, right? So, but there's still some sense of continuity. And so how do we express this? Well, here's a very simple example where we see some kind of continuity property, but we have a change of topology. Okay? So let me consider just the Euclidean space minus the origin, 3D Euclidean space, and the projection onto the last coordinate. So we can view this, so this is a submersion. And so we can look at all the fibers of the submersion. And let me call MS, the manifold MS should be the fiber over the place S. Yeah? So then MS is either R2 minus the origin, if S is equal to 0, or R2. Okay? And let me just choose the Euclidean metric on MS. Okay? So this gives us some kind of continuous family of two-dimensional flat Riemannian manifolds, okay? So which do change the topology as we vary the parameter. So this is so I think nobody everybody would agree that there's some kind of continuity property, and some of these MSs, they are somehow held together by some of the topology of this global space. And so this is what I want to now express more precisely. So for the purposes of this talk, I'll define something that I call a continuous family of manifolds. I'm sure there are other ways of other people have come up with similar notions, but this is some of the terminology that we're using here. So a continuous family of manifolds should be something similar to what I showed on the previous slide. So this is given by a topological space X over which we consider this family, and a collection of smooth manifolds of dimension n, parameterized by S and X. Okay? So these could be like the singular Ricci flows. These could be completely different manifolds. They may have nothing to do with one another. And then I'm going to fix some extra data. I'm going to fix a topology on the disjoint union of all these manifolds. Okay? I'll denote that total space Y. Okay? So I'll find this topology that restricts to the topology on every fiber MS. Okay? And I'll do this in such a way that the standard, and I require that the standard projection should be a continuous topological submersion. Okay? So here's some of the submersion idea that comes back in. Okay? Okay? So now I have some kind of sense of continuity, but what I would also like to do is I would like to express what does somehow smooth dependence, what does dependence in the smooth topology mean if I vary S? Okay? So, and in order to do this, we're going to just use somehow this concept that is used when we look at laminations, for example. So we're going to choose some charts on this total space, which gives us some extra smoothness structures. Okay? So now I'm also fixing a maximal collection of charts of the following form. So these charts, they're more or less they're parametrizations. They go the opposite direction. They are of this form. They're phi s, phi is. And what I do here is I take some small manifold vi, some small smooth manifold, and I'm going to look at some parameterization of vi into ms. Okay? So this depends on S. And it's just a family of, it's just a family of embeddings into ms, parameterized by some small subset ui of x. And I want the following compatibility properties to hold. So first of all, if I view this map as a map from ui cross vi, then this should be a homeomorphism onto its open image. And I want the compatibility condition such that if I look at two such charts and I map from vi into vj for every s, okay? So this may not be defined everywhere. So let me just take the open subsets where this is defined. then this consists of smooth maps from Vi to Vj that depend continuously on S in the C infinity topology, in the local C infinity topology. Okay? So this is a little weaker than saying that we have a smooth submersion. Okay, so if we had a smooth submersion, then we would have a smooth structure on this total space. But we don't have a sense of smoothness for now on the precise total space. We only know whether smooth maps on, we only want to say whether smooth maps on MS vary continuously in the C infinity topology. Okay, so I'm not saying that this depends smoothly on S. I'm just saying it depends continuously on S in the C infinity topology. Okay? Okay. So just, you know, for those people who work more on the topological side, this is essentially a submersion combined with elimination. Okay, okay, this is a continuous family of manifolds. And so how do I define a continuous family of Riemannian manifolds? I could just fix a family of Riemannian metrics on each of the MS, and then I just need to require that these Riemannian metrics are transversely continuous. Okay? So that means, in a certain sense, that if I vary S, then the Riemannian metrics should vary continuously in the C infinity topology. Okay? And this can now be expressed just by pulling back these Riemannian metrics via these charts. Then I get a Riemannian metric on each of these VIs, and I require that these Riemannian metrics depend continuously on S in the local C infinity topology. Okay? So this is how I would define a family of Riemannian, a continuous family of Riemannian metrics. Okay. Okay, and then similarly, and I can do the same for other tensor fields. Okay, so whenever I take a family of tensor fields on this MS, I can just look at the corresponding pullbacks and ask whether they depend continuously on S. And so this now allows us to define what a continuous family of Ricci flow spacetimes is. Okay? So a continuous family of Ricci flow spacetimes is given by a continuous family of, you know, like a structure as I showed on the previous slide on the spacetime manifolds. So so basically given by a continuous family of 4 manifolds, such that the corresponding smooth objects are transversely continuous. Okay? So this is the actual definition. And this now allows us to express continuity of singular Ricci flows. Okay? So let me now state the main theorem. So this theorem now says that if given some, let's assume we are given some closed manifold, 3 manifold, and a continuous family of Riemannian metrics on it, parameterized by some topological space that depends continuously in the smooth topology. Okay? Now then what we can do is for every S, we can choose some singular Ricci flow starting from MGS. Okay? So we can do this uniquely up to isometry. Then, okay, so again, a priori, these flows may not have anything to do with one another, but then we can endow the collection of these flows with a unique structure of a continuous family of Ricci flow spacetimes with the property that somehow the set of time zero slices, such as the trivial family given by, you know, just given by the manifold itself, and the corresponding metrics is just the family GS. It's just the family of initial conditions. And so this is how we can express continuity. And maybe just to recall here, for any the structure allows us to take to look at time slices, and for any time t, the structure will induce a structure of a structure as a structure of continuous families of 3 manifolds, and the family of Riemannian metrics is going to then be transversely continuous as well. Okay, so this also allows us to look at families of time slices. Okay, maybe I'll pause to see if there are any questions. All right, so let's move to the last chapter. So in the last chapter, I want to prove both of these topological conjectures. And so before doing this, there's one annoying thing that we have to deal with, which I'll just use one brief slide to talk about. And this is a called a rounding construction for singular Ricci flow. So here's my observation. So as we discussed several times, if we have a singular Ricci flow and we look at a point whose curvature scale is very small, i.e. whose curvature is very large, then X is locally epsilon modeled on the final time slice of a kappa solution. Okay? And any kappa solution which we know now is either round or rotationally symmetric. Okay? So this means that singular Ricci flows in high curvature regions are almost rotationally symmetric or almost round. Okay? And we're going to take advantage of this roundness or this rotational symmetry. And it's going to turn out to be just much easier to work with precisely round or precisely rotationally symmetric metrics. Okay? So the idea will be in the following: to replace our singular Ricci flows by flows that are almost singular, but that are precisely round or precisely rotationally symmetric. Okay? And so that's why we have to do this kind of pre-processing of our continuous family of Ricci flows. So we'll have to replace it by these rounded Ricci flows. Okay? So the precise lemma it's much longer, much more technical, but let me just give you, show you what the flavor of this lemma would be. So it says that given a continuous family of singular Ricci flows, okay, so we expect that we've already constructed this, and some delta, there are transversely continuous tensor fields, G prime S and del T S, del T prime S, so replacing GS and del TS, such that these flows here form a continuous family of, you could call them rounded singular almost Ricci flows. Okay, so essentially, so what I mean by this, so essentially I want that all the properties of singular Ricci flows hold except for the precise Ricci flow equation, which I'll replace by an almost Ricci flow equation with precision delta. I really don't care anymore whether something evolves by the Ricci flow, because our discussion will be mainly topological from there on. So I can violate the Ricci flow equation. The G prime S and the del prime S will approximate the original metrics and vector fields, respectively. And I want now that at small curvature scales, or where the curvature is very large, G prime S should locally be precisely round or rotationally symmetric, and the flow of this new time vector field should preserve those symmetries. Okay? So if I'm looking at small scales, I want to see an almost Ricci flow that just consists of rotationally symmetric or round metrics. Right. So the proof is technical. That's somehow the best word for it. It's quite long and it's no fun. Okay. So you just first make certain regions of the flow of these flows rotationally symmetric. Then you realize that you can find some kind of canonical rounding procedure and so on. Okay? So you're just working you're working in regions that are almost rotationally symmetric, and you just have to find some canonical way of turning this into precise rotational symmetry. Okay? And so maybe the crux of this lemma is that this can be done in a continuous fashion. Okay? So we really end up with a continuous family of rounded singular almost Ricci flows. All right, so if this is too technical, you can just always assume that our singular Ricci flows are rotationally symmetric for the remainder of this chapter. Okay, so let's try to start with the proof here, or at least give you the strategy that we want to follow. So again, this is the theorem that we want to prove, that the space of PSC metrics and the space of constant curvature metrics are either contractible or empty. And we can prove the contractibility of both of these spaces in the same go. Okay? So you can just replace PSC by constant curvature metric or the other way around to get the corresponding proof. Right. So just to start, let's recall from the two-dimensional proof, how did we prove the statement? And let me look at this two-dimensional proof a little differently. Okay, let me phrase this in terms of homotopy groups. Okay? All right, so we want to show that the kth homotopy group of the constant of either this space or this space is equal to 0. Okay? All right, so how would we show this in the two-dimensional case? Well, we would we would assume that there is a family of a K-sphere of family of constant curvature or PSC metrics that those are given. Okay? And then we could fill in this K-sphere of metrics by a K+1 disk of just arbitrary metrics. Okay, so this is what we've done in the previous case. Right? So assume that we have a map from SK into the set of PSC or constant curvature metrics. Then we can also find a map from then we can extend this map to a K+1 disk, which takes values in the space of all metrics. Okay. Okay, so in the end, we obtain this map, which I'll just express as a family or as a continuous family here of metrics HS0 parameterized by a K+1 disk in such a way that for S in the boundary of this disk, these metrics are either PSC or constant curvature, depending on what we want to show. And so now our hope is to extend these maps to some kind of homotopy. And in dimension 2, essentially the idea was to say, well, this is the initial condition to some kind of Ricci flow, modulo rescaling and reparameterization. So T is essentially the time parameter of the corresponding Ricci flow. And well, what does this Ricci flow do? Well, for time T is equal to 0, we have the initial metric. And then for every S, this essentially modulo rescaling and reparameterization depends on the Ricci flow. And the final metric is going to be a round metric. Right? Okay? So in other words, if we have the following property, HST is PSC or constant curvature, whenever ST is contained in this set. So what does this mean? Well, whenever S is contained, sorry, maybe let me talk about this guy here first. Whenever T is equal to 1, then HS1 should always have constant curvature, which just means that our Ricci flow converges to a constant curvature metric for every S. Okay? So when ST is in this set, which is some of the final end of this homotopy, then HST is PSC or has even constant curvature. And also, if S is in the boundary of our disk, well, then it just corresponds to a Ricci flow, which is either PSC or has constant curvature. Then for any T, HST is PSC or has constant curvature. Okay? Okay. So this metric is basically nice whenever ST is in the subset. So what is the subset? Well, this is essentially the boundary of the product of the K+1 disk and the unit interval. Okay? And so this topologically is an annulus, and this is a disk, okay? A K+1 disk. Okay? So if we take the union of these, then we get a K+1 disk whose boundary is the sphere corresponding to the metrics that were given in the beginning. Okay? So this would give us the desired homotopy, null homotopy. Okay? So again, the metrics that are given due to the fact that we want to show that the kth homotopy group vanishes corresponds to the matrix HS0, where H is contained in the boundary of the K+1 disk. And this set, okay, so this corresponds to the boundary of DK+1 cross 0. And this set is a K+1 disk, is diffeomorphic or homeomorphic to a K+1 disk, which bounds this K sphere. And so this is so this would be, so if we restrict this family to the subset, we get a null homotopy of the given family of metrics. All right, so this is what we can do in the two-dimensional case, because we can really construct these families of metrics easily via the Ricci flow. But in dimension 3, this is what I mean by this time, HS0 only gives us a continuous family of singular Ricci flows, which we can round to produce a continuous family of rounded singular almost Ricci flows. Okay? Okay, so given a family of metrics on the K+1 disk, all we get is this family of rounded singular almost Ricci flows. And so now we need to do something with them. We need to extract some information out of them, which will lead to the desired null homotopy. All right, so what what's the remaining problem? So we basically need to somehow convert these flows into families of metrics on the initial manifold. Okay? So abstractly, what does it mean? So, well, we're given a continuous family of rounded singular almost Ricci flows, M prime S, parameterized by, let's say, a K plus 1 disk, but we can just, for simplicity, let's just say it's any topological space. Then based on these rounded almost singular Ricci flows, we want to find some kind of similar continuous family of metrics, HST, now where S is in X and T goes from 0 to 1, such that we somehow can follow the same idea here. So what do we want to be true? Well, we want the initial condition to be the same. Okay, so that would just guarantee that we're really starting from these metrics, that we're given with. And we also want this property that these metrics have constant curvature or are round whenever ST is in this subset. So we can guarantee this by requiring that H of S, 1 has constant curvature or is PSC. And moreover, we want the same whenever ST is in this subset. And we can require this that by saying that if the corresponding almost singular, the rounded almost Ricci flow, if this has constant curvature or is PSC, then so does HST for every T is from 0 to 1. Okay. So again, if we are able to convert any continuous family of these rounded flows into HST, then we can really just follow the same strategy as before. Okay? So we just have to do this intermediate step that HST is not just the precise Ricci flow. We just have to first construct this rounded singular Ricci flows, and then the corresponding family HST will just be the family that we're looking for. And then we can again restrict it to the union of this annulus in the disk. Are there any questions so far? Okay. So what I want to do in the following, and again, the proof will be the same essentially, no matter whether we want to consider the constant curvature case or the positive scalar curvature case. But just for simplicity here, because we focused on the generalized Smale conjecture, let me focus on the constant curvature case. So let me throw away this for now. Okay. And there's one last step that I want to do. So here's some kind of small simplification. So we want to construct a constant curvature metric in the limit for T is equal to 1. Okay? And so here's a simplification. It turns out that we can replace property 2 by the property that HST doesn't have constant curvature, but is only conformally flat, locally conformally flat. Okay? So why is that the case? Well, if our metric is locally conformally flat, then it's conformally equivalent to a constant curvature metric. Okay? And so if we're given a continuous family of metrics that are conformally equivalent to a constant curvature metric, there's an easy way of somewhat deforming these metrics just by changing the conformal factor to a constant curvature metric. So essentially, instead of going from 0 to 1, we can go from 0 to 2. So we first go from 0 to 1 to construct these families of conformally flat metrics. And then we go from 1 to 2 just by deforming the conformal factor in a continuous fashion to a family of constant curvature metrics, locally conformal, sorry. Okay, so and so this can be done relatively easily. That's somehow a convex problem, so we can always choose these conformal factors continuously. Okay, so let me do this simplification here. Okay, so here's our conversion problem. Just to recap again, we're given a family of these rounded Ricci flows, singular Ricci flows, almost Ricci flows, and we want to convert them into a family of continuous Riemannian metrics on the initial time slice, such that the initial time, that MHS0 is equal to the initial metric, such that HS1 is locally conformally flat, and with this property that if our flow already had constant curvature, then so does HST for all t. Okay? So this is essentially what we want to obtain. So if, again, if our flows M prime S were not singular, if they were just happened to be given by conventional Ricci flows, then we could just choose HST to be the corresponding Ricci flow, appropriately rescaled and reparameterized, and then we're done. Okay? So the difficulty here is to deal with possible singularities. Okay, and so the idea will now to prove this conversion problem by backwards induction over time. Okay, so let me give you somehow the naive outline of how to accomplish this. So I'm going to fix some capital T, maybe possibly very large. So this is some time t. And then my hope is to at least solve this conversion problem such that 2 and 3 are hold, but that instead of starting at time 0, we start somehow at time t. So I want mh as 0 to be the corresponding time t slice. Okay, so my hope is that this metric might be rounder, or these flows may not have existed for such a long time, because we're just taking really the very end of these flows. So it might just be easier to solve this conversion problem if we choose t large enough. And then there might be a way of deforming this HST such that instead of this property, we have the property where t is replaced by t minus some tau, where tau is some uniform constant, small uniform constant. So if we can say that whenever such an HS exists at time t, then we can also construct an HST for time t minus tau. And just by repeating this until we hit t equal to 0, we would get the desired conversion problem. We would solve the desired conversion problem. Okay. But here's the problem. I mean, the problem is that this is too naive, right? So the topology of the space, of course, varies as we change S. Okay? So this property only makes sense because t is equal to 0. Okay? At time 0, all the time slices are have the same topology, and some of this continuous family of time slices is really trivial. For any other time, the family of time slices may be non-trivial because we may somehow cross some singularity. So this property really doesn't make sense. Okay? And so somehow the main idea is now to come up with some new notion and somehow to imitate this idea in such a way that it's mathematically correct and that it somehow still follows this process. And to do this, we came up with a new terminology that's somehow flexible enough to precisely fit our purposes. Okay? And so this terminology, we'll call this a partial homotopy at time t. Okay? And I'll show you the definition on the next slide, but I think more interesting than what the actual definition of a partial homotopy is what are its properties. Okay? So a partial homotopy is essentially something like a family of Riemannian metrics on M that satisfies proposition 2 and 3, as well as this something like this proposition, something like this property. It's some kind of version of this, and it has the following properties. Well, if I choose t very large, then the family of these time slices is just going to be empty, because all these flows are going extinct after some time. So if t is very large, then I can find some kind of empty partial homotopy at time t. And so I can show existence of a partial homotopy at time t for t very large. And then this definition will be flexible enough to allow certain construction moves. So I can alter or modify partial homotopies in such a way that I can take a partial homotopy at time t and use these moves to construct a partial homotopy at time t minus tau. Okay? And then I can repeat this process until I can show the existence of a partial homotopy at time 0. And again, this definition of a partial homotopy is chosen in such a way that the existence of a partial homotopy at time 0 implies the existence of a family of metrics satisfying 1, 2, and 3. Okay? So this is some of the idea here. And so, okay, so now I have to define what a partial homotopy is. Okay? And I'll give you more or less a complete definition, maybe slightly simplified, but so this is just what I want to do in the last slide. So again, the idea again will be to work over a simplicial decomposition of the space. So we assume that X is some simplicial complex. Now for each simplex sigma, what we're going to choose is we're going to choose again these domains C sigma S. Okay? So these should be compact smooth domains. Recall that in the simplified proof, we chose these domains C sigma S, which were basically the manifold minus a few disks or minus a few balls. Okay? Now we have to work in the corresponding time T slice, so we can't project down to the manifold anymore. Okay? So now instead of choosing single domains C sigma in the manifold at time 0, we'll have to choose a continuous family of domains in the time T slice. Okay, so remember these are different manifolds, so we have to somehow move them according to the parameter. Right? So those are defined for every S in sigma. Okay? So essentially, these disks, these domains are going to be chosen in such a way that they stay far enough away from the singular part of the flow. So where somehow the metric is interesting and possibly non-rotationally symmetric. And then we also, so instead of choosing a continuous family of Riemannian metrics on M, we're now choosing continuous families of Riemannian metrics H sigma ST, where S is only taken out of sigma. And we're going to choose these metrics only on C sigma S, right? Not on the entire manifold. And so now it's possible to make sense of these conditions. Okay, again, we want H sigma S comma 0 just to be equal to the metric at time T restricted to this domain. And then 2 meant that HS1 should be locally conformally flat, so this still makes sense. And 3 was that, well, if M prime was round, then so is HST. So this also still makes sense. Okay. So by restricting to small simplices, we somehow made sure, and restricting to domains, we made sure that there's no topological change anymore, and so we could define these guys. Okay. Okay. But now we have different somehow pictures over different simplices, so we need certain compatibility conditions. Okay. So again, we want that if we take a smaller simplex, which is contained in a larger simplex, we want the corresponding C sigma to be contained in the Z tau, just as we've done in the simplified proof. We also need some kind of largeness condition of these domains. So we of course, if these time T slices are sufficiently interesting, we want C sigma not to be empty. Okay? So we want that these C sigma S's are chosen large enough so that the points that are missing are points where the curvature is very small. Okay? And therefore, the components here are either rotationally symmetric or round. Okay? Okay, so we really want to choose these guys large enough so that whatever is missing is just round or rotationally symmetric. So it's not going to be that interesting. And then we want also these different H's, we will only want them to differ by what we call contractible ambiguity. Okay? So in other words, whenever some Z tau is bigger than some Z sigma over the same S, we want the H, which is the H of tau on the larger domain, we want it to be only round or rotationally symmetric there, okay? on these differences. Okay? So in other words, whenever I've defined H, over a smaller simplex, when I've defined it over a larger domain, then the part that's missing over the other simplex should just be round or rotationally symmetric. So, if there's some ambiguity later, I'm only going to be dealing with round or rotationally symmetric metrics, and the space of round or rotationally symmetric metrics is contractible. So I can always make some changes there. So it's not going to cause so many problems. Okay. So this is essentially the definition of a partial homotopy. So now it shouldn't be too hard to see that we have these two important properties. So first of all, if T is very large, if chosen very large, so that all these guys here are empty, then we can just choose all the Z sigma S to be empty. So this is just the trivial partial homotopy. So for large T, there is always a partial homotopy at time T. And then if T is equal to 0, well, then this condition means that C sigma S has to be MS0, okay? Because we assume at time 0 that the curvature is somehow bounded by some constant. Okay? So if C sigma S if all the C sigma S are the same over a point, or I should say they are equal to M, then we can just fit together all these H sigma ST to give us the desired HST over M. Okay? So this would, so then so in other words, a partial homotopy at time 0 implies the existence of a family of metrics HST. And so now we need to somehow argue how can we move from time T to some time 0. Okay? And so it turns out that this definition is flexible enough to allow these modification moves. Okay? So what kind of moves can we carry out? So first of all, we can always pass to a simplicial refinement and then find the corresponding objects Z and H. We can also enlarge Z sigma S by a family of round or rotationally symmetric subsets. So this is important when we pass through a neck pinch. Okay? So after we've passed through a neck pinch, we have this neck that we need to add back into Z sigma S. And so we need to do this from time to time. And so the idea is, well, whenever we have to add a subset, that was a subset that was just, that was just singular or almost singular a step ago. And so therefore it still needs to be rotationally symmetric. And then we can just add this back in. And due to this contractible ambiguity property, it's somehow possible to do some kind of extension over the skeleton. We also sometimes need to shrink these domains by removing disks. So this is important that if we move backwards in time, and let's say we move backwards in time and we're getting closer to a singularity. So we see these kind of caps arising. So if we go backwards in time, so then we may have to remove a disk. And this is actually the hardest step. So we need to remove a disk over maybe some simplex, while maybe keeping the disk in over the other simplex, and then maintaining this property is non-trivial, but it's possible. And then lastly, we should be able to move somehow the entire partial homotopy backwards by one time step. Okay? And so the idea is to will be somehow is to follow these modification moves essentially in this order. Right? So we first pass to simplicial refinement so that these flows at time T don't change too much. Then we enlarge, we add in some component C sigma where the flow has become macroscopic. Then we shrink some C sigma so that where the curvature is too small or is too large, the curvature scale is too small, so that if we so that we can move these C sigma S's backwards in time, and then we move backwards in time because we're going to stay away from the almost singular part. Okay? And so in this step, we basically concatenate these HSTs by the corresponding almost Ricci flow, rounded Ricci flow. Okay? And so again, after iterating this procedure, we can start with some empty partial homotopy, and we obtain back a partial homotopy at time 0, which solves the problem and then proves the theorem. Okay, I think that is maybe all that I want to say. So I think I think that's all I wanted to say about this. Sorry, I don't have any more theorems, so maybe I'll stop a little early today. Thank you for your attention, and if there are questions, please don't hesitate to ask.
Yeah, thank you very much. So are there questions or even comments? Nothing in the room? Not much on the chat. So anyway, we thank you very much. Yeah, this I agree with Alessandro also.
Thanks.
There is a question by Antoine.
How big is the set of singular time? So that's a good question. So we don't know in any examples where the set of singular times is bigger than finite. But some of the best known bound is that the set of singular times has Hausdorff dimension at least 1/2, at most 1/2, no bigger than 1/2. Okay. And that's not hard to see. You have to somehow follow certain x backwards in time. So so the best bound is the Hausdorff dimension is less or equal to 1/2. I hope that answers your question. Oh, Jason, yes. Sorry, I forgot to post the Dropbox link. Let me do this now before the Zoom window disappears.
So in the meantime, I thank you for these wonderful lectures. In fact, we are very interested by the details, to be honest, and the analytical details as well as the details that you gave today are very interesting.
Oh, thanks.
And this is a wonderful piece of work. So for the other people, I recall that next week Richard will give a lecture on Tuesday evening for us. That is 5:30 p.m. Paris time.
Okay.
And you can, well, if I remember well, in any case, the schedule is posted, so you can check. This is exactly that. And so, well, it's my pleasure to thank you again, and everybody share this pleasure.
Yes.
And nothing more to say that have a nice weekend, and we meet again next week.
Yeah. Thanks again for letting me do this talk, giving me so much time to go over the details.
We could give you more if you wish.
Okay. I'll send you again the handout slides, slightly improved, and have a great week.
We will take care of this. To post them. Okay. See you next week then. Bye bye.
See you next week. Bye.